Section 8.4, Bond Polarity and Electronegativity. When two identical atoms bond, as in chlorine or hydrogen, the electron pairs must be shared equally. In highly ionic compounds, on the other hand, such as NaCl, there's relatively little sharing of electrons, which means that sodium chloride is best described as composed of sodium ions and chloride ions. The 3s electron of sodium is, in effect, transferred completely to chlorine. The bonds that are found in most substances fall somewhere between these extremes. The concept of bond polarity helps describe the sharing of electrons between atoms. A nonpolar covalent bond is one in which the electrons are shared equally between two atoms, as in Cl2 or N2, examples we just cited. In a polar covalent bond, one of the atoms exerts a greater attraction for the bonding electrons than the other. If the difference in relative ability to attract electrons is large enough, an ionic bond is formed. Electronegativity. We use a quantity called electronegativity to estimate whether a given bond will be nonpolar covalent, polar covalent, or ionic. Electronegativity is the ability of an atom in a molecule to attract electrons to itself. The greater an atom's electronegativity, the greater its ability to attract electrons to itself. The electronegativity of an atom in a molecule is related to its ionization energy and electron affinity, which are properties of isolated atoms. The ionization energy measures how strong a gaseous atom will hold on to its electrons, while electron affinity is a measure of how strongly an atom attracts additional electrons. An atom with a very negative electron affinity and high ionization energy will both attract electrons from other atoms and resist having its electrons attracted away. It will be highly electronegative. Numerical estimates of electronegativity can be based on a variety of properties, not just ionization energy and electron affinity. The American chemist Linus Pauling developed the first and most widely used electronegativity scale. He based his scale on thermochemical data. Figure 8.6 shows Pauling's electronegativity values for many of the elements. The values are unitless. Fluorine, the most electronegative element, has an electronegativity of 4. The least electronegative element, cesium, has electronegativity of 0.7. The values for all other elements lie between these two extremes. Within each period, there's generally a steady increase in electronegativity from left to right. That is, from the most metallic to the most non-metallic elements, with some exceptions, especially within the transition metals. Electronegativity decreases with increasing atomic number in any one group. That is what we know because we know the ionization energies tend to decrease within increasing atomic number in a group, and electron affinities don't change very much. You don't need to memorize numerical values for electronegativity. Instead, you should know the periodic trends so that you can predict which of the two elements is more electronegative. Electronegativity and bond polarity. We can use the difference in electronegativity between two atoms to gauge the polarity of the bonding between them. Consider these 3 fluorine-containing compounds. F2, nonpolar covalent. Hydrogen fluoride, or hydrofluoric acid, polar covalent. Lithium fluoride, ionic. In the fluoride, the electrons are shared equally between the fluorine atoms, and thus the covalent bond is nonpolar. In general, a nonpolar covalent bond results when the electronegativities of the bonded atoms are equal. In the hydrofluoric acid, the fluorine atom has a greater electronegativity than the hydrogen atom, with the result that the sharing of the electrons is unequal. The bond is polar. In general, a polar covalent bond results when the atoms differ in electronegativity. The hydrogen fluoride as more electronegative fluorine atom attracts electron density away from the less electronegative hydrogen atom, leaving a partial positive charge on the hydrogen atom and a partial negative charge on the fluorine atom. We can represent the charge distribution as H delta positive, fluorine delta negative. The lithium fluoride of the electronegativity difference is very large, meaning that the electron density shifted far towards fluorine. The resultant bond is therefore more accurately described as ionic. This shift in electron density towards the more electronegative atom can be seen in the results of calculations of electron density distributions as shown in Figure 8.7. The regions in space that have relatively higher electron density are shown in red, and those with a relatively lower electron density are shown in blue. You can see that the the distribution is symmetrical. In hydrofluoric acid, it's clearly shifted towards fluorine, and in lithium fluoride, the shift is even greater. These examples illustrate, therefore, that the greater the difference in electronegativity between the atoms, the more polar their bond. Dipole moments. The difference in electronegativity between hydrogen and fluorine leads to a polar covalent bond in the hydrogen fluoride molecule. As a consequence, there is a concentration of negative charge on the more electronegative fluorine atom, leaving the less electronegative hydrogen atom at the positive end of the molecule. A molecule such as hydrofluoric acid, in which the center of positive and negative charge do not coincide, are said to be a polar molecule. Thus, we describe both bonds and entire molecules as being polar and nonpolar. We can indicate the polarity of the hydrogen fluoride molecule in two ways: delta positive, delta negative, or arrow pointing to delta negative. Recall from the preceding subjection that delta positive and delta negative indicate the partial positive and negative charges on the hydrogen and fluorine atoms. In the notation on the right, the arrow denotes the shift in electron density towards the fluorine atom. The crossed end of the arrow can be thought of as the plus sign that designates the positive end of the molecule. Polarity helps determine many of the properties of substances that we observe at the macroscopic level in the laboratory and in everyday life. Polar molecules align themselves with respect to one another, with the negative end of the one molecule and the positive end of the other attracting each other. Polar molecules are likewise attracted to ions. The negative end of the polar molecule is attracted to the positive ion, and the positive end is attracted to the negative ion. These interactions account for many properties of liquids, solids, and solutions that you'll see in chapters 11, 12, and 13. How can we quantify the polarity of a molecule? Whenever the distance separates two electrical charges of equal magnitude but opposite sign, a dipole is established. The quantitative measure of the magnitude of a dipole is called its dipole moment, as denoted by mu. If the distance r separates two equal and opposite charges, q1 and q positive, q negative, the magnitude of the dipole moment is the product of q and r. The dipole moment increases as the magnitude of charge that's separated increases and the distance between the charges increases. For a nonpolar molecule, such as fluorine, the dipole moment is zero because there's no charge separation. Dipole moments are usually reported in debye, a unit that equals 3.34 times 10 to the negative 30 coulomb meters. For molecules, we usually measure charge in units of the electronic charge, E, 1.6 times 10 to the 19 coulombs, and distance in units of angstroms. Suppose that the two charges, positive 1 and negative 1, in units of electron, are separated by a distance of 1 angstrom. Then the dipole moment produced is 4.79 debye. Measurement of the dipole moments can provide us with valuable information about the charge distribution in molecules, as illustrated in sample 8.5. Table 8.3 presents the bond lengths and dipole moments of the hydrogen halides. Notice that as we proceed from hydrofluoric acid to hydroiodic acid, the electronegativity difference decreases and the bond length increases. The first effect decreases the amount of charge separated and causes the dipole moment to decrease from hydrogen fluoride to hydrogen iodide, even though the bond length is increasing. Calculations identical to those used in sample exercise 8.5 shows that the actual charges on the atom decrease from 0.4 positive to 0.4 negative in hydrogen fluoride to 0.057 positive and negative in hydrogen iodide. We can visualize the varying degree of electronic charge shift in the substances from computer-generated renderings based on calculations of electron distribution as shown in figure 8.9. For these molecules, the change in the electronegativity difference has a greater effect on the dipole moment than does the change in bond length. Before leaving this section, let's return to the lithium fluoride molecule pictured in figure 8.7. Under standard conditions, lithium fluoride exists as an extended ionic solid with an arrangement of atoms analogous to the sodium chloride structure shown in figure 8.3. However, it is possible to generate lithium fluoride molecules by vaporizing the solid at high temperature. The molecules have a dipole moment of 6.28 d and a bond distance of 1.58 angstroms. For these values, we can calculate the charge on lithium and fluorine to be about 0.857 plus and minus respectively. This bond is extremely polar, and the presence of such large charges strongly favors the formation of an extended ionic lattice whereby each lithium ion is surrounded by fluorine ions and vice versa.